Hi, welcome to the Aerospace Maker channel. I'm Aaron Harper. This channel is all about the nuts and bolts of aerospace. This week we were going to cover the communications link from the ground station antenna all the way through the system, but conversations made me realize that we need to cover noise and antennas first. We'll pick up on the ground segment next week. If you have not seen this series' previous videos, I encourage you to view them and see how we arrived at the figures and assumptions rather than just take our word for it. Now there's going to be a fair bit of details, so refer to the website aerospacemaker.org for the transcript with the references at the end. Now should you get lost during this whole mess, don't panic. Just replay the video a couple times and dig a little deeper into the source material. That's what it's there for. Now let's review what we know so far. In our scenario, we received the images from the NOAA 19 weather satellite. Assuming our satellite is 60 degrees above the horizon at an altitude of 870 kilometers above the surface of the Earth, transmitting at a frequency of 137.1 megahertz. From the first video, we also know that the satellite's output power is 12.45 dBW, or decibels per watt. That's the estimated isotropic radiated power, or EIRP. Now, last week we determined that our slant range is 985.192 kilometers, and this attenuates or reduces the signal by 135.06 dB. The atmosphere has an additional attenuation of minus 0.566, bringing the total loss of signal to minus 135.626 dB. When combined with the EIRP of the satellite signal, we get a signal level at the ground station of minus 123.176 dBW, or decibels per watt. Now, this is not a strong signal, and we have the tools to make up for the losses, but there's more than just distance in our way. Now, going back to last week's analogy of seeing a flashlight on a distant mountainside, while the signal is faint, it may well be detectable under ideal conditions. What do we mean by ideal conditions? Well, if it's at night, or, for example, if the room that we're in is darkened, we have a good chance of seeing the signal. However, if it's during daylight hours, or if the lights are on in the room, the odds are we're not going to see that signal. We're not going to see that light on the distant mountainside. That's because all the extra light around us is interfering with our ability to see it. As if receiving a small signal isn't difficult enough, noise from various sources can make it like finding a needle in a haystack. The signal from NOAA 19 is very faint, and unless conditions are ideal or near, or made as close to ideal as possible, we will not be able to gather enough signal to decode it into a meaningful picture. Now, fortunately, there are tools to detect weak signals, such as this waterfall display. Now, there is a satellite signal in that noise in that display. It is a curved dashed line a little to the right of center in that waterfall display. This and other tools only show us the signal. They don't make the signal easier to receive. Now, noise is difficult to avoid, and reducing it while boosting the signal we want is tricky. We need to understand noise and its sources to mitigate it. Simply put, noise is any signal which is unintended in either a transmission or reception system. As such, it can be anything from a microwave oven to a machine shop 2 miles away. It can be our own sun, quasars in our galaxy, or even the Earth itself. Now, besides man-made sources, anytime atoms are in motion, they make noise. The more atoms, the more noise. Also, the more heat, the more motion, and thus, more noise. The measurement of noise is Kelvin, the temperature measurement. Now imagine trying to overhear what I'm saying when a bunch of maracas are playing. The more they vibrate back and forth, the less you're going to be able to hear. There are many sources of noise which interfere with our ability to bring in the weak signal. Now, they're generally very broad across the frequency domain or broadband, with the exception of the interfering radio transmissions. The following are sources with their anticipated levels, called noise temperature. Galactic sources. Now, they vary from 10 to 250 Kelvin. The cosmic background is 2 Kelvin. That's the remnants of the Big Bang that we see. Our own atmosphere is 32 Kelvin. The Earth is 290 Kelvin. And the Sun is 300,000 Kelvin on a quiet day. Now, man-made noise varies from near zero to 4,500 Kelvin in industrial areas. And then equipment noise will vary by equipment and ambient conditions and so on. Some noise sources we don't really have to worry about. For example, the Earth is a fairly strong source, but if we point our antenna patterns upward and separate the antenna from the ground by a ground plane, it will not be as much of an issue. Some noise sources are best dealt with by avoiding them altogether, such as avoiding industrialized areas in setting up our ground station and not pointing an antenna at the sun. Now, unfortunately, the noise present is not only amplified with the signal, but parts of our equipment generate their own noise through RF interference. Shot noise or Johnson-Nyquist noise. All these are various types of electronic noise that our system introduces. Since all of these noise effects are thermally dependent, one effective way to reduce the system noise is to cool the components. Interference can be reduced by shielding the stages that might generate or be susceptible to the interference in a shield. Now, a shield is like a metal cap that sits over the top, and its function is to shunt the interfering signal to ground and therefore significantly reduce the effects. These methods, though, they only go so far in reducing interference and system noise, which is why it's important to move the signal from the analog to a digital format where there is less loss as soon as possible in the signal stream. The atmosphere itself can also make noise as the molecules rattle around. While this effect is fairly minimal compared to other noise sources, it adds up, particularly if the signal is coming in at a shallow angle. You have more atmosphere to go through. The lower the angle, the more atmosphere, which not only attenuates our signal, as we saw in a previous video, but it also adds noise. Now, for our purposes, we're just going to use 32 Kelvin as the atmospheric noise figure, as this is fairly close to what it will be in reality. Now, as you might suspect, noise from celestial sources, or what they call sky noise, varies by what you're pointing at. In this image, 3 radio wavelengths are rendered by 3 colors. While beautiful, the powerful radio emissions near the center of our galaxy shining brightly will increase the noise floor, making a weak signal much more difficult to pick up. More specific to our scenario, this image shows the sky at a frequency of 408 MHz, and 137 MHz is fairly similar. You can see how the areas correspond roughly to the composite image we saw earlier. The colors represent the background noise temperature on a logarithmic scale from 10 Kelvin in black and blue to 250 Kelvin in red. Pointing an antenna at a satellite with the center of the galaxy as a backdrop will increase the system noise by over 3 dB. With a weak signal, this could become quite significant, even make or break the link. But there is nothing to do for it other than wait for the satellite to move. For our purposes, let's use 15 Kelvin as our sky noise figure, as this is very close to the median. Now, if we could point a perfect beam at a satellite, we would not have to worry about terrestrial noise sources. But we don't live in a perfect world. Antenna patterns not only have the primary or major lobe, they also have side and back lobes called minor lobes, as you can see in this plot. Most likely, 1 or 2 of these minor lobes will be pointing at the ground, which, as we discussed, is 290 Kelvin, or worse, at an industrial center, 1200 Kelvin, or the computer used to decode the signal, 890 Kelvin. Now, Murphy's Law being what it is, your neighbor will pick the time for the satellite pass to begin welding his latest metal art masterpiece. This is why antenna selection is so critical. We need to not only make sure you can pick up the signal, but also not pick up the noise. Antenna efficiency is a figure between 0 and 1, which indicates how much of the signal is coming from the major lobe compared to the minor lobes. It factors heavily into the gain characteristics of the antenna. Now, unfortunately, this figure is not often published even by antenna manufacturers, since few people understand what this figure represents. It's much easier to sell an antenna which yields a 400% boost, or 6 dB of gain, than saying it has an efficiency of 0.73. In this example, an antenna has a fairly narrow major lobe, and this particular model has an efficiency of 0.88. This means that 88% of the signal the antenna has converted to electrical power is coming from the satellite, the atmosphere, and the celestial objects in the major lobes pattern, while the other 12% is coming from the minor lobes. Unfortunately, this probably includes sources like the industrial area near the ground station or other terrestrial noise in the Earth itself, in addition to the ever-present celestial sources. The noise added to our signal is a function of the average noise temperature picked up on all lobes of our antenna, with the gain of the lobe factored in, using the antenna efficiency numbers as a factor. We'll step through this on a future video. Okay, we want to be able to pick up NOAA 19 at 60 degrees above the local horizon while rejecting the terrestrial signals. We also want the overhead signal, so a top blind antenna design like this one is a very poor choice. What we need is an antenna pattern closer to this. This pattern would reject much of the terrestrial noise while giving us a fairly good signal in our anticipated 120 degree detection arc. What determines the pattern of the antenna is largely construction, so this becomes a process of finding the pattern which matches our use. Now, unfortunately, there really isn't an antenna pattern library online or a database, so this becomes more of a process of trial and error and going through other people's designs until you find something you like. In doing the research, 3 antennas have the pattern we are after: the egg beater, the turnstile, and the quadrifiliar antennas. The quadrifiliar can have higher gain, but it's a bear to design and kind of difficult to construct. So we'll try the cheapest and easiest to build antenna first. The egg beater fits this bill, so that is what we'll base our math on, and if the math works out, that's what we're going to build. While the antenna is a fairly low gain design, 5 to 6 dB of gain, the lack of any minor lobes make it very tolerant of noisy environments and easy to figure out the pattern as the satellite flies over. Well, that's it for the noise and antenna selection part. Next week we'll cover the communication link from the ground station antenna all the way through to the receiver. Now, besides commonly available parts, the equipment we hope to use is the inexpensive RTL2832U software-defined radio SDR receiver that connects to any modern computer via the USB port. The unit I'll be using is the Newelec NE-SDR Smart, which is based upon the RTL2832U and the RT820T2 tuner. I ordered it a couple days ago and expect it shortly after the 4th of July holiday. Now, for about $30, this SDR has some bells and whistles that help us bring in the signal and do so with less noise and so on. But once we get it all figured out and tested, I'll build the same ground station using the less expensive model to make it work for much less money. I get this feeling that several antenna designs will be made in the course of this video. Now, if you want to get a jump on things, go ahead and order one online. The software to run this device is generally free and easy to get online for any operating system, and will become a core component of the ground station receiver we're going to build. If you do pick one up, make sure that it has the R820T or the R820T2 tuner, as this combination yields great results. As far as the software to run the SDR and decode the signal, it all depends on what operating system you're running on your computer. Now, I use Linux. This means that GQRX and G&E Radio are some of the tools I use. We'll be using GQRX to receive the signals from NOAA 19, which also works on Macs. Now, if you're a Windows user, have a look at SDR Sharp and HD SDR. All of these software titles are free. If you get one of the SDR dongles and want to get familiar with running the radio, install the software and start exploring. Let's go. I would like to send out a big thanks to Scott Johnson over at SolarNet One for the use of a proper video camera and a generous donation. This guy and his company are awesome. Right now he is setting up computers for use in Kiribati, a South Sea island group. He's helping those folks have access to the internet resources we all take for granted. Now, if you need help with a power or you need a networking miracle for anything from a home to a sovereign nation, call Scott over at SolarNet One. Please like this video, and we welcome any and all feedback. If you like the channel, subscribe so you don't miss a thing. And visit our website, aerospacemaker.org. As time goes on, more and more information will be presented there. To support the channel and accelerate improvements, please donate to us through the Patreon link below.